In this video lesson, we are going to complete this part or this submodule of this section on atomic structure. And in order to do that, we are going to recall that the Standard Model classifies matter into quarks, leptons and bosons. We're going to discuss the nature of the strong nuclear force or the strong force, the weak nuclear force or the weak force, and the electromagnetic force. We're also going to refer to the gravity force, even though it does not fall directly into the Standard Model yet. I would like to just note that for the sake of the course that we're doing, or the syllabus that we're doing, the IEB further studies in physics, we are not going to refer to the strong force, but formerly the strong nuclear force and the weak nuclear force. In the big wide world, scientists often refer to the strong force and the weak force without explicitly stating that they are nuclear forces. We are also going to identify which exchange particles or force carriers are associated with the types of forces. So here is a table of the baryons that we have referred to in earlier video lessons, and as we have learned that baryons are made up of 3 quarks, and depending upon the composition of the flavor of quarks that particular baryon has determines what type of baryon it is. So the most common ones that we work with are the proton, which consists of 2 up and 1 down quark, and the neutron, which consists of 1 up quark and 2 down quarks. But as we've learned, there's a multitude of other quarks, and these quarks you would not be expected to learn their compositions off by heart. We would give you a table. When it comes to mesons, we worked explicitly with the pi plus and the pi minus and the pi zero, also referred to as pions. We also referred to the K0, the K plus, the K negative, also known as kaons, but there are other mesons as well, as you can see in this table, and this is not a complete table of all the mesons available. But what we do know about mesons is their quark composition consists of 2 quarks, always 1 quark and of one flavor, and then an antiquark of a different flavor. We also get these quarks here, which have the various mixtures of these combinations. So here the Standard Model is represented in a visual way. So we have the 6 flavors of quarks here: up, down, charm, strange, top, bottom. And this is first generation, second generation, which is heavier, third generation, which are the heaviest. We have the leptons, which are the electron and the electron neutrino. We have the muon and the muon neutrino. We have the tau and the tau neutrino, and here 2 first generation, second generation, third generation, and they get heavier as we go that way. Notice that all of these leptons have antiparticles, and all of these also have antiparticles, the antiquarks. So the quarks and the leptons, they are what we refer to as matter particles. They follow or behave according to Fermi-Dirac statistics. They have half integral spins, and we can classify them, the quarks and the leptons, as in that way as well. So those are fermions, the matter particles. This side here is interesting, and this is where our focus is going to be in this video lesson. So we have the bosons. Now bosons follow what they call Bose-Einstein statistics. If you go further and study at university, you'll do statistical mechanics somewhere in your undergrad, and you will learn about Maxwell-Boltzmann statistics, about Fermi-Dirac and Bose-Einstein. Now, if we look at these bosons, these are gauge bosons, and these gauge bosons are the gluon, the photon, the Z boson, and the W boson. And these are the bosons that we are going to look at in detail, relevant to the forces that they are part of, or they are the force carriers of, or the exchange particles of. And then we have what is now the famous Higgs boson, which many people have come to learn as the God particle. That's what we call a scalar boson. So the Standard Model explains how elementary or fundamental particles of matter, those are the fermions, interact with each other through the fundamental forces of nature, except gravity. So we have the fermions, as we've discussed. They can be classified into quarks and leptons. They're the matter particles. The bosons, they are the exchange particles or the force carriers. In 1935, a Japanese physicist by the name of Yukawa suggested that the forces between particles are mediated or transmitted by gauge bosons. So on school level, we can think of these as vector bosons. Gauge physics is something that exists beyond undergrad physics. If you go and you study particle physics on honors level or master's or PhD level, and you deal with what they call quantum field theory, you will also deal with gauge mathematics. So, but for grade 12, grade 11 and grade 12, we can think of these as vector bosons as opposed to scalar bosons. And he said that each force has a different range and a different boson which establishes the range. So this was an amazing hypothesis. So the gauge bosons are also virtual particles. That implies that they cannot be detected during the exchange between the particles interacting with each other. So as the rest mass of these gauge bosons increases, it implies the time that they can move between particles interacting without being detected decreases. So the heavier the gauge boson, the shorter the range, so that they remain undetected. So there's an inverse proportionality or negative relationship between the rest mass. When we talk about the rest masses, that's the mass of the particle when it hasn't got extra mass, energy, or perceived mass due to it traveling at super high speeds, relativistic speeds close to the speed of light, which results in a mass dilation and higher mass due to a mass dilation. So that now is part of what we would call special relativity. So in essence, without getting too complicated, the higher the mass of the virtual boson, the gauge boson, the shorter the range. So the gauge bosons are the gluon for the strong nuclear force, the Z0, the W plus, the W minus for the weak nuclear force. We see that it in actual fact has 3 exchange particles, and the photon for the electromagnetic force. Now we would associate photons with light, but remember that light is part of the electromagnetic spectrum and is associated with the electromagnetic force. But this would be a virtual photon as opposed to a photon of light. The scalar boson is the Higgs boson, which explains how elementary particles acquired their mass in the early universe when interacting with the Higgs field. Looking at the 4 fundamental forces in a little bit more detail, the gravitational force, which you learn about in grade 11, can be described according to Newton's model as the force equals the universal gravitational constant, which is 6.63 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the one particle times the mass of the other particle divided by the distance squared. So the gravitational force has an infinite range, which would then imply that the graviton, which is a proposed virtual boson for the gravitational force, would have a zero mass. If it has an infinite range, then it has a zero rest mass. The graviton has yet to be found. If it were to be found, it would be one of the great discoveries of the 21st century. We have discovered gravitational waves, which Albert Einstein postulated more than 100 years ago. So who knows, maybe we'll find the graviton. If we do, it will then mean that the gravitational force becomes part of the standard model. So if we look at it, at the gravitational force, and we look at the fact that the force is directly proportional to the product of the masses, we can then understand why it's only when the masses are of an astronomical scale that this very small universal constant actually is overcome by the mass, the product mass, that it actually becomes significant. So on quantum level, we find that the masses of our particles are so small that the gravitational force is actually negligible. The force of gravity is inversely proportional to the distance squared between the centers of the masses. It's only attractive, and as I've mentioned, it's only dominant. It's the dominant force on the astronomical scale. It is only really dominant on an astronomical scale. However, when one deals with a black hole, where your scale of your black hole inside is on a quantum level, or it's proposed to be on a quantum level, and you have immense gravitational fields, that there's where the quantum and the gravity theories come together. And someone like Stephen Hawking spent most of his professional career studying quantum gravity. So this is one of the reasons, one of the main reasons why black holes are so fascinating to study, is because they are extreme phenomena where the quantum world and the gravitational world are forced together. The theory of gravity that we ascribe to now is Einstein's theory of general relativity. And that is in actual fact a macroscopic scale, where gravity is seen as the distortion of the space-time, which is a four-dimensional space-time fabric of the universe. When you have a very big mass, you can think of it as being dropped onto this four-dimensional rubber mat, and the heavier it is, the deeper it will fall into the four-dimensional space-time, and therefore create a greater curvature. And the curvature of that space-time is gravity. So instead of viewing gravity as a force, it's viewed as the curvature of space-time. The problem at present is that we don't have a fully accepted theory yet that merges gravity with the standard model and the forces associated with it, the weak nuclear force, the strong nuclear force, and the electromagnetic force. Maybe one day one of you will discover it and win the Nobel Prize for physics for that. So it's negligible on atomic and subatomic scales unless you're dealing with black holes, and the graviton, as I've mentioned, is a hypothetical force carrier. The electromagnetic force mathematically looks very much the same, but this is a force. There's some differences, because firstly, if you look at the Coulomb's constant as opposed to gravity, which is of the order of 10 to the minus 11, this is of the order of almost 10 to the 10. So it's almost 20 orders of magnitude bigger, the constant, I'm referring to the constant now, of gravity. So this is a much, much stronger force, and it's exceptionally strong, especially over short distances. It also has an infinite range, and the reason for that is the virtual photon has a zero mass. It acts on charges and magnets, and it's attractive and repulsive, and that is why, albeit that it's so much stronger than gravity, we don't experience it on a day-to-day basis because of the fact that positive and negative charges attract and negative charges repel, and positive charges repel. And so within systems like atoms and molecules, they actually cancel out. So you don't have a net force that we experience outside of the systems which have immense forces inside them, but the net forces cancel out because the electromagnetic force is attractive and repulsive, unlike gravity, which is purely attractive. The photon is the force carrier, and we're talking about a virtual photon now, and it has a zero mass. So the strong nuclear force is very strong. It has a very short range of about 10 to the minus 15 meters, which is the order of the protons and neutrons diameters inside the nucleus. The strong nuclear force acts between hadrons. Now remember, hadrons would be baryons and mesons. So it acts on particles that have quarks in them, but it does not act between leptons. It's attractive at approximately 10 to the minus 15 meters, but it's strongly repulsive at ranges less than, or distances less than 10 to the minus 15 meters. So it too has an attractive and a repulsive nature. Gluons are the force carriers. That's therefore the strong nuclear force is also referred to as the gluonic force by some, and it's responsible for nuclear stability. So I would like you to appreciate this. If you think of the nucleus, it's made up of protons, which are positive, and neutrons, which are neutral. So strictly speaking, if you purely look at it from an electromagnetic force perspective, we know that like charges repel. So the protons should repel. The neutrons don't have charge. So in actual fact, the nucleus shouldn't exist. It should actually explode, as it were, as the protons repel each other. However, on that scale, you have the strong nuclear force, which is an attractive force which pulls them together, gluing the protons and neutrons together. This is one of the reasons why there's so much energy, nuclear energy, locked in the nucleus of an atom, because of the strong nuclear force. And so if we start to fiddle with it, as it were, if we start to rearrange the composition of the nucleus and we start to disturb this force, if I can use that term, then it unleashes huge amounts of energy. The weak nuclear force is obviously weak, and it's a very short range force, approximately 10 to the minus 18 meters. Now, we have never measured the diameter of an electron, but if the electron were to have a diameter, it would be less than 10 to the minus 18 meters. It acts between all particles. The W plus, W minus, and the Z0 bosons are its exchange particles. It's responsible for radioactive decay and neutrino interactions. The W plus and the W minus are also responsible for flavor changing in quarks and leptons. So here is a handy summary of the forces and the exchange particles and their relative strength and range. So we see the gravitational force, which is not actually part of the standard model. It's interactions between particles with mass. The proposed exchange particle is the graviton. Its relative strength compared to the strong interaction, which is assigned a relative value of 1, is 10 to the minus 41. So you can see how weak it is in comparison to the rest of the forces. Its range is infinite. The electromagnetic force is between particles with electric charge. Its virtual exchange particle is the photon. Its relative strength is 1/100th of that of the strong force, strong nuclear force. Its range is also infinite. The strong force is between quarks, and by extension particles made out of quarks, hadrons. The exchange particles are gluons and also mesons. But the fundamental exchange particle is a gluon. The relative strength is 1. It's assigned that. It's the strongest of all. And it has a range of 10 to the minus 15 meters. The weak interaction, it's between quarks and leptons. It's only responsible for beta decay. W plus, W negative, and Z0 bosons. It has a relative strength of 10 to the minus 6, so it's 1/1,000,000th the strength of the strong force. So it's weaker than the electromagnetic, but much stronger than the gravitational. Its range is 10 to the minus 18, which would mean that it has virtual bosons that have a rest mass that are much higher than the rest. So having completed this now, we have looked at the standard model, we've looked at the quarks, the leptons, we've looked at hadrons, which are made up of quarks, the baryons and the mesons. We've looked at how the conservation laws of charge, baryon number, lepton number, need to be conserved in order for an interaction to be viable. And we've also looked at the forces associated with the particles, the matter particles, the fermions in the standard model, their ranges and relative strengths. And so with this, we finish off this section on the structure of matter.